Thank you. Thank you, everybody, for joining. I'm going to talk today about the rise of evil robots. So I already was presented. I can tell you about myself two more things. I am Romanian, born in Bucharest, and I like whiskey, especially smoked one. So today I'm going to talk about the rise of autonomous systems. Basically, we are living in a new industrial revolution. I will call it 4.5 or 5.0. I will showcase why safety and security are better together, and they are the last guardians to prevent evil autonomous systems for breaking the laws of robotics. So let me start with some historical facts. So humanity started long ago with Industry 0.0 by harvesting animal muscle power and starting communicating verbally. And then moving to Industry 1.0, we've seen mechanization, water power, steam power, and introducing writing. Industry 2.0 is basically what our grandparents and our parents live. It is the mass production, assembly line, and electricity. And today we are living during Industry 3.0, so the computer, electronics, and automatization. And Industry 4.0 basically is the IoT, cloud, big data. So we are blessed to live in this area of three industry revolutions, and we're starting to see the beginning of Industry 5.0. It brings us cognitive computing, AI, autonomous systems, robotization, robots with human-like capabilities, human-robot co-working, and additional things like bioeconomy and quantum computing. I want to focus today on autonomous systems. Probably when you see or hear about an autonomous system, you think about autonomous driving car, self-driving car. But basically an autonomous system, it's a system composed of hardware, firmware, and software, a complex system that is basically trying to solve a problem by performing a predefined specific action. For a system to be considered an autonomous system, it must be able to gather information for an environment, for example, to find a solution alone based on this information, and to execute an action to achieve a goal, a predefined goal. Historically, this is not a new thing. So the first one to invent an autonomous technology was Leonardo da Vinci in the 1478. It is basically invented a self-propelled cart. And over the history, we have missiles, planes, metro, and more than 10 years ago, a self-driving car. But today, I want to talk about more about the robots, robotic systems. And I will focus especially on autonomous mobile robots. But in the robotics systems, Tesla was the first that invented that a century ago. And I want to mention just the Spirit and Opportunity mobile robots that are harvesting the Mars. And of course, we have additional usages in military and, as they're going to showcase, in other domains. This revolution of the autonomous systems basically is standing on four innovative technologies. So first, if you have an advance in sensor technology. The sensor that we have today, they are much, much stronger, sophisticated, and enables those systems to sense the environment. Of course, we have the artificial intelligence and the machine learning, and better and more strong connectivity and communication between those systems. And on top of that, we have new enhanced safety systems. The autonomous systems basically are, as I say, very complex. They are usually composed from many, many subsystems. You can have a safety system, cybersecurity system, self-driving systems, multimedia, and on top of that, they are communicating and relying on the information from the environment from many other sensors. so lidars and lasers and cameras and specific radars. So the more complex those systems are, the easiest to break them eventually. And we don't have only just self-driving cars. We have planes, spaceships, submarines, drones that are used basically in the day-to-day delivery, in surveillance, unfortunately in military usages as well. On top of those use cases, I just wanted to show you two examples. One is from Boston Dynamics and the other is from Menti. So sporadic, random example of new types of autonomous systems. So humanoids, robots that are looking like humans, and they're gonna be with us in the next couple of years. This is, those two examples are already in mass production and are expected to be sold in 2025 for home assistants, healthcare, and other manufacturing usages. Okay, so this is crazy. Those are a fully autonomous system that will be side by side. I personally did some research around autonomous mobile robots. They are already here. So those are mobile robots that are used in many domains like warehouses and manufacturing, in agriculture. And unlike self-driving cars that you can find in some specific areas and you still are near the control, those mobile robots are already with us for the last 3, 4, 5 years. The full autonomous systems are already existing. Those are like a small little car that can move a payload from a few hundred kilograms to up to 3, 4, 5 tons. So imagine that those systems are already autonomous, moving around, working, existing side by side with humans. So they actually can hurt human beings if somebody can hack them and break them. And I will show you that those are very easily hackable today. And of course, we're going to discuss how to protect against those. The slides will be available after, so feel free to picture, but there will be, the slides will be shared. So as I show, those very sophisticated systems that are autonomous and self-moving around, they are already here, existing. This is not a science fiction speech. And if we're looking on the most critical cybersecurity trends from last year, we can see that the cyber physical systems basically take a very good place, the 10th place, and they are focusing on autonomous systems, and they are basically explicitly required to add robust security measures such encryption, authentication, and monitoring in order to prevent those systems to be abused. And maybe now it's a good time to quote Isaac Asimov. I want to focus on the most important 3 laws of robotics. He had more than those 3. So first of all, a robot may not injure a human being. So makes sense, and the robot may obey the orders given by a human being. This also makes sense. And the robot must protect its own existence. Okay. So if you're looking on those autonomous systems, they also must follow those 3 fundamental laws. They must accurately read from the physical world through their sensors and actually perform some specific tasks, so write, and never harm human beings. So this is what we expect. So you're probably going to say, well, those systems have safety measures. They are built with safety mechanisms that will prevent them to harm the environment. Am I right? So not long ago, 15 years ago, a small malware called Stuxnet was raised into the world. For you, some of you that may not know it, it is a very famous malware, one of the first that basically abused some centrifuges in nuclear plants in Iran, and what this malware actually did, it tampered with the configuration of the centrifuges in such ways that it spin it so much or spin it too low and cause those centrifuges damage. So basically, this is the first attempt, successful attempt in the history that showcased that a malware can abuse and attack and overcome the safety systems. Okay, so we can't rely on safety systems. And now I will show you that basically those autonomous systems are already hacked and hackable. So my first example is basically in a hospital domain, there are some robots that are moving specific medical supplies and medicine between different departments and delivering the medicine to patients. And basically, the researcher found that those are very hackable and easy to take control. They managed to leak the camera stream and the information that those robots accessed, and basically move them around, change their tasks, and even managed to create those robots into the hospital personnel. So Trend Micro also did the research and also showed that industrial robots are easily hackable, and the attackers can basically alter control parameters, tamper with the calibration, and alter robot states. And basically all those can cripple the production and damaging the machinery and the property, and even injuring employees. Another university research showed that other robots can also be hacked from remote, that the researcher took control of the robots and moved them around. So those are some few examples, but attackers can do much more things. For example, we have a ransomware called Hackerblitz. So during the COVID, universal robots were used to do disinfection in the healthcare industry, and the attackers put a ransomware on those robots to control and cause the denial of service that basically influenced the health services during a real healthcare crisis. And if we're moving forward, less than a year ago, self-driving cars that were tested in the US, we found out that they are basically collecting data and sending it back to the mainland. And that's why one of the reasons that the legislation in the US are banning those autonomous vehicles in the US. As I say, those robots are very used also in agriculture. So imagine huge robots that are controlling the food supply chain, and attackers also showcase that can tamper with them and basically cause a disruption in the food supply chain. So the attacks are real. And in order to understand why those attacks are real is because the systems are very complex. This is a high-level abstraction of a system. So we usually have an autonomous robot that has some sensors, a compute module, a control module, usually communicating to some local server. This is basically a server that is delegating tasks to those robots, those systems. But the problem is that this is not just the end of it. Those systems are eventually connected to other systems, to other enterprise systems, and even to the cloud. And if you're doing a deep dive in those entities, we can see that on the software side, on the robot software side, we have a lot of additional building blocks. We have many components and subcomponents. They interconnect over some connectivity like Wi-Fi or 4 or 5G. And on the server side, again, multiple building blocks. Some are coming from third parties, some are internally developed. And as more ecosystems, there are many additional tools used to calibrate those robots, to update those firmware and software packages, to do simulation and much more. Just one simple robot, you can see that it may have more than one compute. It may have a CPU, a GPU, it may have multiple sensors relying on from, for example, camera and LiDAR and GPS and other. And if you're going up to the stack on the OS level, they usually run Linuxes, either robotic specific OSs or other type of Linux-based OSs. And on top of that, we have a rich ecosystem of third parties and custom-made software packages. So, understanding that, let's talk about the type of the attacks and what basically the attackers want to achieve and how we can mitigate those. So the attackers usually will try to tamper with the control parameters and the calibration parameters. They want to change the production logic, and they probably gonna try to fake the robot signal and the user perceived robot state and the robot state itself. Mainly, they'll try to do a denial of service. They're going to disrupt the manufacturing facilities because this is the most significant economical impact. So, tampering with the production line, tampering with the outputs of the production line. In some cases, they're going to do ransomware schemes, device hijacking, maybe install botnets, but they're going to also look for physical damage. Because in many cases, physical damage will impact the manufacturing brand or the enterprise that is using those robots brand. So I'm going to do a layered approach of how the attacks try to attack those systems and how we should mitigate them. So if you're looking on the software and firmware packages, basically the attacker will try to roll back those software and firmware packages to vulnerable versions. Of course, the mitigation, it's usually to implement secure boot and anti-rollback and avoid those type of attacks. They will also try to load malicious software or firmware calibration files. In the autonomous systems, those are different type of files, and they are specific to each environment and deployment environment. So this is very important to sign those software or firmware calibration and configuration files. It's easy to say, not easy to achieve, but it is something that we should seek to do it. We saw attacks that try to abuse the OTP through OTP wear-out, so implementing and being aware of OTP wear-out is important. So there are types of OTP wear-out protection. Over-the-air attack vectors, they can delay deployment of software updates, and they probably going to try to change commands and parameters that the robots retrieve. So we need to assure that those are passed encrypted, and we should avoid the tampering with those. Additional attacks are through the web management interface. So the goal is to limit those interfaces as much as possible and to use the secure access for those. You would think that those robots are in a controlled environment, but I show you that they can be in a very remote environment, hospitals, agriculture, outside. So, sorry about that. So it's important to control the communication to those robots. They are never isolated. They usually are connected, and it's important to protect basically from the network attacks. So attacker can sniff the network and be doing attack class, man in the middle. They can do that through insecure communication, and basically they can abuse unstable network or deny least topology networks. In many cases, I saw that vendors, they also do hidden connection. Basically, third-party vendors have hidden channels back home for usually software updates or telemetry. Those channels can also be abused. So in order to mitigate that, we need to, of course, emphasize secure communication, use a well-defined topology, do a network segregation, and do component isolation. We basically recommend to utilize firewalls at each system in the network, so each autonomous system should have its own firewall, and also use a firewall at a network level, and also use an identity detection system. And of course, we should monitor for abnormalities. So, on top of that, we also have hardware attacks, because those robots, as I say, they are usually not oversized, so we can basically control them. They can act remotely. Some hardware attacker can come near those robots, can access their buses. They can steal the storage, the memory. They can abuse the unprotected login through basically local ports, serial ports, debug ports, and such. So it's very important to secure the buses, to disable all unused interfaces, and secure the one in use. For example, if you are in those systems, we have sensitive information. The robot perceived information is stored on those robots, so it's important to do disk encryption. And any local access should be protected. I would say probably only enabled to remote access, and using, of course, SSH, certificate-based. Another attack vector is the software development pipeline. So there are a lot of supply chain attacks, and the attackers can abuse third-party vulnerable components, and also if we look on different usages in the industry, we can see that those autonomous systems use deprecated and insecure packages. So the idea is basically to do secure development lifecycle, to basically follow the secure code guidelines, to run, of course, vulnerable scanners, static code analysis, binary scanners, and basically deploy only the reduced needed software components. So in order to reduce the attack surface, we look on different robots. We find huge amount of frameworks, development frameworks that basically were used for development of those robots and not needed on those robots. So the goal is to use a very, very small amount of software components in order to reduce the attack surface. And of course, scanning the pipeline as well. OS level. So usually we're going to see that the vendors are utilizing insecure OS, deprecated OS, end-of-life OSs, and including the third-party packages in use. And the attackers will try to abuse those vulnerable executable. The goal is to mitigate them by doing OS hardening. OS hardening, it's, I would say, not an easy task to do, but it's well-defined domain, and if you're using an OS, it's very important to do an OS hardening, to run antivirus scans, malware detection, rootkit detection on those. Any executable that are installed on those systems can be hardened through secure compilation flags or kernel security settings, and it's better to always continue patching those OSs as well as their third parties. And as I said before, at the OS level, it's important to remove the unneeded software packages and services. So reduce the attack surface by using tine and lean OSs. And in many cases, it's important also to move to non-monolithic approach, basically separating between the kernel and the user space. Another attack vectors of those autonomous systems are the sensors. So you're probably going to say we have camera, lidars, radars, ultrasound. They are all capable for being spoofed. So for example, the camera can be attacked through infrared beams. The lidar and GPS can be spoofed. The attackers use laser reflectors. They can play with the light. And as I said before, they can also tamper with the software and firmware and calibration data of those sensors. The mitigations here are basically never rely on one sensor type. This is a defense in-depth approach. In the autonomous system, basically, in some cases, we are required to use safety versions of those sensors, like safety cameras or safety lidars. Not in all countries this is mandatory, but the industry going in this direction. And the most important is basically to test for all the corners in-house the development phase and not relying on something that will happen at the operation. So basically it's failing safe and secure. So in any corner case, the system should fail safe and secure. And as I say again, sign all the calibration data and the software and the firmware packages in order to verify them before apply. One last but not all is basically protecting the identity and access management. So many attacks are abusing those systems because they have no authentications. They are open by default. And even if we're moving forward and looking for more secure systems, we see that they have weak authentication systems. Sometimes the credentials are embedded, so it's break one, reuse for all. So the mitigation here is, again, those systems should have strong authentication, good passport policy, including a passport rotation. They need to have more than one role. So we saw those systems running with admin privileges, one role. It's in order to separate that, we can have multiple roles. One is for the robot, one is for some integrator, and another for some administrator. So the goal is to run with least privilege. And there should be brute force protection mechanism in place. So till now we've seen that basically those systems are very complex. They are multi-layered and multi-dimensional. And easily the attackers will look for the easiest path in. And there is no other way to do it other than doing a defense in-depth approach. It's putting security layers one after the other. So even if an attacker will break one of the layers, he will still have many other layers to break. So think about a lobster. It's very strong from outside and very tasty inside. One protection layer. We need to have multiple protection layers. So never rely on one layer. So I want to return back to the safety and security. If you're looking on safety, what safety it's looking for, it's the SAI, the safety, availability, and integrity. And when we're looking on security approach, we're looking on confidentiality, integrity, and availability. But on those autonomous systems that are safety and rely on safety, the security should take cover over the safety. In those cases, you will see that they complement each other, but there is no basically safety without having a secure system. So safety is looking to protect the environment from a given system, where the security is trying to protect the system from the environment. When you do approach to those systems, it's important to have a unified safety and security risk framework. So you do risk analysis based on also safety risks that can be there. So safety alone can be happening without having a secure system. Those autonomous systems are very complex, and that's why we need to first make them secure, and then they will be safe. The sources of safety hazards are plenty. It can vary between human and control errors. They can be mechanical failures, time pressure, environmental, and others, but also through unauthorized or malicious access. And take into consideration that if a system is abused and hacked, an attacker can mimic and fake all the other reasons and cause those safety systems to crash. That's why, in order to protect the safety systems, we need to do network security. So again, network isolation. We need to have authentication and authorization for the safety components. Many safety components are user password protected, but they are the same user and password protected that you can search for them in the internet. And again, break one, reuse all. Usually the vendors not changing those or don't care about those. Software and firmware updates and patch management, they must be secure through secure software or firmware update. We need to sign their configuration. So let's say I have a safety camera, I have a configuration that will detect an object into 3, 4, 5 meters from a specific distance. If I can tamper with those configuration, those sensors are basically not useful. The robot will crash into some individual. The last two are two principles that are more safety-oriented, so they should be isolated. Usually the safety systems are isolated from the other systems. So navigation and object detection, they can be basically a very complex system, but the safety system should be isolated. And usually they require to have a duplicacy, so a redundancy duplication. Never rely on one system alone. What I suggest here in this speech, I would say that if those systems are required to have safety certified system, it's also okay to rely on additional safety complementary controls. So for example, I have a safety camera, I can put an additional sensor to double check it. So in order to have those systems secure, there are a lot of activities that we need to do, starting from security design and threat modeling and going through many steps. And you can see here that there are three entities. There is the manufacturer, the integrator, and the operator. So those systems are never developed by one entity, integrated by the same entity, and used by the same entity. And those security activities are common in many cases for more than one entity. So this is important to understand that protecting those systems, it's a shared responsibility. It's basically responsibility of the manufacturing, integrators, and also operators. If I, as a manufacturer, will not develop a secure system, it's game over. In the integration phase, if I'm not going to do an integration correctly, not configure the system to be secure, it's game over. And as an operator, if I'm not going to use the system correctly, it's a game over. So this is one of the other problems, that it's a shared responsibility, not always easy to accomplish. And between more than one vendor. Okay, so connecting to the previous slide, let's see the increased usage of AI in those autonomous systems. So we are using AI today in perception and sensing, in decision-making, in predictive modeling. We are using the AI in simulation, in map generation, in interconnecting with those autonomous systems. And all those are use cases, and some of the use cases that you can see in those autonomous systems. But we are moving forward, so from regular software to auto-generated software, and the future will be basically that those systems will have integrated AI agents. So looking historically, we started from manual execution, then we moved to semi-automated, to automated, then to semi-autonomous. Today we are living with autonomous systems side by side, and in the near future, we're going to see symbiotic autonomy. Basically, those are systems that are not just autonomous, they are fully autonomous, meaning that they can interconnect with other systems, collaborate with other autonomous systems or not autonomous systems. They can work side by side with human beings, and they don't need to be controlled from remote. They are reacting to the environment. So imagine a healthcare assistant robot, or a manufacturing robot that knows that he needs to move things around when the merchandise is arriving in some place, and he needs to take it and do some perceived action. So fully autonomous without any control. And basically, before we can let the robots to take over, we need to do better security and safety. Otherwise, we need to protect them against themselves and hackers, of course, because otherwise, basically, we'll basically creating the Skynet, and we're going to let them control us. The next robot revolution. Okay, so to summarize, it's important to do secure by design. I showcase here that robotics and autonomous systems are, it's a growing domain, and it's still an immature field. They are very complex, and we need to do security from the initial design all the way to the robot implementation and robot integration and usage. All the entire ecosystems must be taken in place, because just one of those layers, if they are not doing the security activities and protecting those systems, they are breakable. And basically, I would say it's important to constantly identify new specific threats and test for new vulnerabilities and ensure that the existing controls are still good enough and not required to be updated. And we need to progress them more and more, because this is an evolving domain. What was secure today, it isn't secure tomorrow. So, if you want to take something from here today, design your systems for both security and safety. If you have safety systems, remember that without security, they are not safety at all. Any autonomous system, it's very complex, so it must follow the defense in depth principle. And if you have such system, it's always a shared responsibility. If you are a developer, it's not ending with you. There is the integrator and the operator at the end. And of course, there is no future without investing in safety and security. So if you're doing similar system or you want to collaborate, feel free to contact me. And thank you for being here. And this is the time for questions.
Thank you very much, Dan. We have questions.
Yeah. Hello, thank you for the great talk. I have a question. Are there any regulations or standards coming to this field of autonomous robots? I saw that the field is in a way immature. I come from automotive field, where you have for cybersecurity some regulations, standards now, and also for functional safety. If you don't consider this, you cannot homologate your car. So, thank you.
Yes, so this is a great question. So, unlike automotive, where it is regulated, the industrial robots, they don't have specific regulations. There is ISO 66423 or something like that. But if they are considered safety systems, those safety systems are regulated. They do have standards that they must follow. But the autonomous system as an overall, in for non-external roads, they are not regulated. Definitely not in China, and this is an evolving domain. For example, I will take an example that somebody approached me with some startup with autonomous small vehicle that is moving like a small golf cart that is moving autonomous on the road. So it or on the near the pedestrians. So we couldn't say if it is a car or it is an autonomous robot. And they must follow definitely the car because they can move on the road. But if it is not in the road, if it is in a manufacturing environment or warehouse environment or agriculture, nobody cares still. But it's an evolving domain.
Thank you. Senior.
Hello.
Hello.
Can you please elaborate on the OS part? You had a line that was stating executable hardening.
Yes.
Thank you.
So at the OS level, we can use so let's divide that in two layers. The OS should be configured with specific settings like ASLR, so address randomization space, meaning that and to protect those executable from unsecure execution. Our software components that we are putting inside those robots should be compiled with security compilation flags that they mitigate specific attacks on those executable. So if you compile with, for example, Stack Canary or 45 source or other flags, those executables are more secure against buffer overflows and such. On top of that, there are kernel settings not always enabled to protect the OS executables as well.
Thank you.
Hello. I have a question.
Yes.
A bit earlier in your presentation, you said that when they are developing this thing, they use outdated systems.
Yes.
How, or in your opinion, what measure they need to be taken to make sure that, for example, a robot who performs an operation on a brain doesn't start to behave like the centrifuge in Iran?
So we saw in different robots that they are using deprecated OSs or deprecated packages like ROS1. It's a framework for robotics, and now there is ROS2, and the ROS2 has also security. So the idea is not to use deprecated packages, and if those robots were developed with such deprecated packages, they must be updated and upgraded, because the time evolves, those systems are, those OSs and third-party packages are hacked, they have vulnerabilities. If not patched, you have a dangerous system running around.
And who's watching the regulator?
So it's not yet a regulated domain. It's, again, an emerging domain. In many factories, they are only looking on the safety mechanisms so that they are safety certified. Making a system safety certified, it's good, but nobody's looking if it is security certified.
Thank you.
Yeah.
Thank you. Senior, coming.
Thank you, Dan, for a fantastic presentation. Question, you mentioned the different types of attack, like hardware, software, operation systems. As a user or operator, what is these areas I should be most sensitive or curious about based on your research? What's based on real life scenarios that you have seen? What's the, what's the trends? What's the most unattended security?
So what I did, I presented the attacks on different layers. But as an operator, let's take it, I'm using such robots. Insecure networks, basically, I see that those robots are utilized in networks that are communicating with other systems. So doing network isolation, having an isolated network, it's also a good practice. Insecure access to those robots, they come open by default or with same username and password for all vendors. So you can search for it on the internet, you will find the username and password. And there are plenty additional things that they should, again, keep them patched, do the secure updates, verify who is doing that, who is accessing those robots. Physically, those robots are really very hard to be protected. So by manufacturing, they must come with some security protection in place. Operator can be responsible of protecting physical access, but everything else, it's more on the operator side as well.
Hi, thank you for the presentation. I think one aspect that would be pretty important would be the physical security of an operator,
Yes.
for example. Meaning, okay, I don't know, to have a certain distance from a robot, to have like an emergency button or something. So I think these measures are also very important, besides all the, aspects related to the OSs, how the code is done, updated, etc. It's also this physical protection that gives the operator trust that, okay, he can work side by side with the robot, What's your perspective on this?
Yes,
side?
so in some picture maybe so there are safety buttons or safety mechanisms, but I show you that they can be overcome. The safety button usually are isolated, not connected to anything, because they're dumb and simple. You just push the button, stop the robot. But Other safety mechanisms like LIDARs or cameras, they are really connected and doing additional things. Only the safety features of those are isolated. So, first of all, you can't really keep a distance because they are intend to work nearby you, and I have some other videos that you can see a robot is moving around, saw you, moving around and continue to do its work. So the idea is you not need to be afraid of those robots, but you must somehow be sure that they are really secured. Those are not autonomous guided robots, AGVs, or vehicles, that they have their own, path, that they can work on this path, and if you are on the path, this is your problem. They are fully autonomous. So imagine your vacuum cleaner at your house. They are the same, but with more insights and fully autonomous capabilities, and big. So.
Coming.
Hi, I'm here. My question was about, you talk about an autonomous vacuum cleaner.
Yeah.
How about in a hospital, it would be used as an entry point in a more secure network, or to end up engaging with another device which has a security at a higher standard, let's say?
So
you use indirectly a robot who's less developed, like you said, the vacuum cleaner.
So what's the question again?
If you ever observed using undeveloped robots, like you said, to access more important systems like entry points.
Okay, so you're saying, okay, I understand your question. So you ask if attacks use those systems to do a lateral movement into other systems. So, and you bring up the hospital robot, for example. Yes, usually attackers will reach those systems through additional servers that are connected to them. But in some cases, they can also attack those robots and do the lateral movement. Again, in this talk today, I gave the autonomous mobile robot as an example for autonomous systems. I personally have a product that is around autonomous robot systems, but you can think about any smart connected IoTs and apply all the same things that I showed today on those systems. The only difference is that they are autonomous and they must be protected, so they have safety systems inside. That's the only difference, but usually this is the same approach. Either attack from another connected system, or if an attacker gains an access in one robot, he can usually basically move between the other robots and the server and additional systems that are connected. Usually they send insights to some BI server in the enterprise, and they get some task to do from some server connected in the enterprise. So this is an attack vector as well. Yeah.
Thank you very much.
Thank you for the question.
And another one.
Are you doing usually the test for these robots to see the weakness, let's say, in front of potential attackers? And if you have in place the, let's say, the procedure, if it's happened to a robot to escape from our control and to turn against us.
So I showcased, first of all, let's answer the second part. All the examples that I showcased really happened. So attackers control the robot, crash it into the people. It's either showcased or it happened through the attacks. So this is already happening 2 years, 3 years ago. Because as I say, unlike the fully autonomous cars, those autonomous robots are here with us in the airports, in the hospital, in the warehouses and manufacturing. About the first part of the question. Let's take an autonomous system, as an example, an autonomous mobile robot. I dissect the verification in several cases. software level, network level, and such and such and such. It's easy to test. You can test it during the development. You can test it at the integration phase. Usually the operator, the consumer can also bring its own assessment team to test them. What is more complex to test is how the robot will behave in some corner cases if somebody tamper with the sensors. This is not an easy task to do. This is more on the vendor responsibility, and there are some certification aspects that require to do that. Usually they don't do that, but this is the tricky, to test the robot in many, many corner cases that you may not imagine that they may happen. As I say, you operate a robot in a closed environment, but suddenly there is a light like a flash or something, and something can obscure the sensor, and he will not see a person in front of you, and he will collide. So you must test that in your validation labs or manufacturing environment somehow. This is crucial, and we find plenty of issues around sensor snooping and tampering with the sensor insights and such.